Okay, so we are going to review nuclear chemistry in chapter 21, and I'm going to go through this fairly quickly because honestly, a lot of it, until you get toward the end, is just a review of Regents Chem. Jot down any notes on your note packets that things that you may have forgotten or that you want to recall later. So I think the best way to understand how radioactive dating works is to look at carbon dating, because you know that all organic material that's either currently living or once living contains carbon. And the half-life of carbon is about 5,700 years. So it's limited then to objects that are no more than 50,000 years old. After that, there's too little of the carbon-14 left that you can't actually detect how much is in there. You can try using other isotopes such as U-238 or lead-206 in rocks, but for organic material, we can go back about 50,000 years. So how does that happen? How do we measure the amount of carbon that is in a once living organism? Well, you have to go back to how did the carbon get there? So cosmic rays, the sun, okay, which is largely made of protons, enters the atmosphere and it collides with atoms and it creates neutrons. So now we have free-floating neutrons in the air. Those neutrons then are captured by nitrogen. And when that happens, we release a proton and form carbon-14. Carbon-14 then gets incorporated into carbon dioxide. Well, what do plants use? Plants use carbon dioxide in the process of photosynthesis. And then in photosynthesis, right, things grow. We know that. And animals eat those things because they are herbivores. And then we buy them. Like we buy hamburger and we buy vegetables. So we then ingest carbon-14. Once an organism dies, that ingestion or intake of carbon-14 ceases. So you have that amount in your system. And it's going to decrease through beta emission over time. And when it does that, it forms nitrogen 14(7). We can then measure that amount and determine how old that organism is. Interesting enough, there is a way to measure the rate at which a sample decays, and those are named after the two scientists that studied them. Henry Becquerel and Marie Curie won the Nobel Prize for discovering evidence of radioactivity. So it makes sense that this would be named after them. So you have the Becquerel, BQ, which is 1 disintegration per second, and the Curie, CI, which is 3.7 times 10 to the 10th disintegrations per second, which is the rate of decay of 1 gram of radium. You've probably heard of a Geiger counter. We talked about that in Regents Chem, and that's the most popular way of measuring radioactivity. But we can also use what's called film badges and phosphors, or scintillation counters. As I said, Henry Becquerel first discovered evidence of radioactivity, and it was because of the radioactivity producing a fog on a photographic plate. The darker the fog means the more exposure to radioactivity. So that's going to produce dark spots on the developed film. Film badges are currently used by people who work with radioactivity to measure their own exposure to something over time. So here you can see the film strip is white before radiation exposure, and then you can see in the middle the film strip darkens, and you can see what your dose is, so what your exposure is. So some people actually work in an environment. I mean, obviously they work with protection, but they still need to know how much the person's been exposed to for safety reasons. A Geiger counter measures the amount of activity present in a radioactive sample. So the radioactive substance enters a window and creates ions that are in a gas, and those ions are transposed into an electric current that is then measured and recorded by the instrument. So I don't know how well you can see in your diagram, but you can see all the way on the top right where the radiation, so either alpha particles, beta particles, or gamma rays, penetrate the window. Then inside the tube, the radiation ionizes gaseous atoms. So this means it could be argon, it could be helium. So it causes them to ionize, which means what? They're going to lose an electron. Then those charged particles, or ions, move between the anode and the cathode and create an electric current. Then that current is measured by a series of pulses. Usually here it is, okay? And then the greater the radiation, the greater number of pulses. The last one is called phosphors. So some substances have the ability to absorb radioactivity, and when they do that, they emit light. These are called phosphors. An instrument commonly used to measure the amount of light emitted by a phosphor is called a scintillation counter. It converts the light emitted by the substance to an electronic response for measurement. I will put on Schoology in this same folder a few short video clips that goes into more detail about these, because these don't really show you pictures of it. So I thought it was interesting, so I'll put them there as well. And you can watch them after the video. Radiotracers are used to study a chemical reaction. These are radioisotopes. We use these a lot in medical diagnosis, and then the element can be followed through a reaction to determine its path and understand the mechanism of a chemical reaction. Radionuclides react chemically exactly the same as a non-radioactive nuclei of the same element. So it doesn't change the way that it reacts. So usually, as I said earlier, the radioisotope will have a very short half-life. It can be administered usually intravenously by IV and then followed. Some you actually drink. So there is a barium radioactive drink that tastes kind of like chalk, and when you drink it, they can follow the path all the way through your digestive system into your small intestines, your large intestines, to see if you have some type of blockage. Others are done IV. So sometimes a woman might have a problem with her fallopian tubes. They can inject a dye into the fallopian tube and watch the dye travel through the tube to see if she might have a blockage or something going on in her tube, especially if she's experiencing infertility problems. Certain elements collect more in certain tissues, so an organ or tissue type can be studied based on where the radioactivity collects. So that's another thing that they can use it for. So we've talked about iodine-131. It's used for the study of thyroid. I said its half-life earlier was about 8 days. They had it listed as years, 0.022 years. They do not have cobalt listed here, which is usually used for cobalt-60 for the study of cancer. They do have iron-59 for red blood cells, phosphorus-32 for eyes, liver, and tumors, technetium-99 for heart, bones, liver, and lungs, thallium-201 for heart and arteries, and sodium-24 for the circulatory system. And you can see here, relatively speaking, the half-lives are very short because, again, we don't want this stuff hanging around in our bodies for a very long time. Another example of the use of radiation, specifically positron emission, is in the PET scan, standing for Positron Emission Tomography. A compound is labeled with a positron emitter, and it's injected into the patient. Blood flow, oxygen, and glucose metabolism and other biological functions can be studied. The labeled glucose is used to study the brain, as seen here on the right. So here's the what happens is the radioisotope emits a positron. That positron is then detected by scintillation counters. They detect gamma rays. And those gamma rays are produced as a result of when a positron collides with an electron. And all of these happen microscopically. You cannot see it happening. But what appears on the image to the technician is what you see in the bottom right-hand corner. You can see a normal scan on the left. You can see mild cognitive impairment in the middle. And then you can see Alzheimer's disease on the right. So why is this important? Well, when you think about it, as you get older, one of the common problems that older people have is atherosclerosis, which is a common cause of narrow or blocked blood vessels. Now, this could be used due to cholesterol buildup, calcium, which causes hardening of the arteries. Then that will cause reduced blood flow to the brain. When that happens, when you have less oxygen and blood flow to the brain, that causes swelling and lesions and helps cause what's called, and you don't have to know this because this is more medical terms, but I just want you to understand, beta amyloid plaques, and that's hallmark features of Alzheimer's. So, in a way, you leading a healthy life and eating healthy can help reduce Alzheimer's in some respects, because if you don't have hardening of the arteries and those things associated with high cholesterol and calcium buildup, you'll have maximum blood flow to the brain. I'm not saying you're never going to get Alzheimer's, okay, but I'm just saying this is one of the underlying causes that could help reduce that. All right, let's change direction here. We're going to talk about energy in nuclear reactions. So there's a lot of energy stored in nuclei, and you've all taken physics, so you're all familiar with Einstein's famous equation, E equals mc squared, which directly relates the mass of a substance to the speed of light, which results in energy. To show the enormous difference in energy for nuclear reactions, the mass change associated with alpha decay of 1 mole of uranium-238 to thorium-234 is negative 0.0046 grams. So let's look at this change in energy. So you've got your mass, your difference in mass, times the speed of light, which is negative 4.1 times 10 to the 11 joules, or 410 billion kilojoules. Remember, negative means just that heat is released. So that is a lot of energy. So where does the energy come from? You know, according to the law of conservation of matter, that energy, the law of conservation of energy, Well, let's talk about mass too. we'll do both. The law of conservation of matter tells us that matter can't be created or destroyed, simply rearranged from one substance to another. So what we start with, what we have to finish with. Same goes for the law of conservation of energy. Energy can't be created or destroyed, can simply be arranged from one form to another. What one system loses, theoretically, another system has to gain. Those are for chemical reactions. They do not apply to nuclear reactions, which is what we are talking about. In nuclear reactions, what has been observed time and time again is that the mass of the nuclei after the reaction is less than those of the individual parts going into the reaction. That mass difference is called the mass defect. Some of the original mass is converted to a whole lot of energy. The energy needed to separate a nucleus into its nucleons, its protons, and its neutrons is called the nuclear binding energy. So let's look at the difference between the mass defects and the binding energies for the three nuclei here. First, we're looking at an alpha particle. So regular mass of the nucleus, you see 4.00150. Mass of the individual nucleons, 4.03188. That means your mass defect is 0.03038. That's the difference in the nucleus and the mass of the individual nucleons. Then you have a specific binding energy. That binding energy is going to be different depending on the nucleus that you're dealing with. So in this case for alpha, it's 4.53 times 10 to the negative 12. Therefore, the binding energy per nucleon, what you see there, 1.13 times 10 to the negative 12. So all we did there to get the binding energy per nucleon is take the binding energy and divide it by 4, which is the number of particles in alpha. And the others would work the same way. So how does this nuclear binding energy affect nuclear processes? Heavy nuclei gain stability and give off energy when they split into two smaller nuclei. That's fission, fission-division. So uranium-235, splitting into barium and krypton. Lighter nuclei emit great amounts of energy by being combined, fusion. So your hydrogen isotopes, your tritium, your deuterium. As I alluded to earlier, there are two different types of energy, chemical versus nuclear. Chemical energy is simply that associated with breaking bonds and making new bonds. The energy I start with, I have to finish with. Nuclear energy, however, is vast in comparison. And nuclear energy is due to the changes in the nucleus of the atoms when they change into different atoms. 13% of worldwide energy now comes from nuclear energy. You can see here a comparison of France, United States, China, and worldwide. You can see that France leads the world in the use of nuclear energy. 76% of France's energy comes from nuclear energy. Next is the United States, not even in mere comparison, with 6%. And then China, 5%. China still relies heavily on the use of coal, almost flip-flopping with France. They better figure it out soon or they're not going to have any energy in the future, because coal is becoming a finite resource. All right, let's look at nuclear fission. Commercial nuclear power plants use fission. They take heavy nuclei and split it. I mentioned earlier uranium-235 splitting into barium and krypton, which you see there. It can also be split into tellurium and zirconium, as you also see here. How do we do it? We bombard it with a neutron. Okay. The second reaction, barium and krypton, is more effective because you're producing 3 neutrons as opposed to 2 neutrons. Those 3 neutrons then go find another uranium atom. Each one of those will then bombard another U-235. Those 3 will then produce 3 more. So now at the second reaction you've got 9 neutrons. Whereas if you're splitting into tellurium, zirconium, you only have 2. So then you're going to only have 4 at the next reaction. As I said, that bombardment of the radioactive nuclide with a neutron starts the process. And then those neutrons then strike another nuclei. And that produces their decay, causing more neutrons. And then we wind up with a chain reaction. This happens repeatedly, and it happens very quickly. This is showing you the first one, the tellurium and the zirconium. Neutron hits a nucleus. You produce 2 neutrons. Each of those neutrons then go find another nucleus to hit, producing 2 more. So at this second stage where you have 4 neutrons, if you were using barium and krypton, you would have 9. These words on this page in bold are important. The minimum mass that must be present for a chain reaction to be sustained is called the critical mass. If you have less than the critical mass, then the reaction will not continue. So you can see what's called subcritical mass. Subcritical mass, the rate of neutron loss is greater than the rate of neutron creation by fission. The reaction will not be sustained. In a critical mass, the rate of neutron loss equals the rate of neutron creation by fission. And then if you have more than the critical mass present, where your rate of neutron loss is less than the rate of neutron created by fission, an explosion will occur. So weapons were created by causing smaller amounts to be forced together to create this mass. This can be purposely done when we're talking about nuclear warfare. In nuclear reactors, the heat generated by the reaction is used to produce steam that in turn turns a turbine connected to a generator. Otherwise, the plant is basically the same as any other power plant. So let's take a closer look at this. You have a primary reactor core where pressurized water is heated in the reactor core. This heat is then transferred to a secondary coolant in the heat exchanger. That generates steam. That steam is important. It goes through a condenser, which brings it back into, well, first of all, the steam drives the electric generator, but it does go through a condenser, which then turns it back into water. And then that water is then cooled by going into a river. Okay, that's what causes it to condense. And then it can be pumped back into the steam generator again to be repurposed as steam. An important part of the reactor core are the fuel rods, control rods, moderators, and coolant. This is part of the reactor core where it all starts. The water acts as a moderator and a coolant. You have your fuel elements and you have your control rods. The primary role of the control rods is to block the path of some of the neutrons because we don't want it to reach that supercritical mass. That means nothing good. Explosion time. From time to time, the reactors need to be stopped periodically to replace or reprocess the nuclear fuel. These are usually stored in pools at the reactor site. The original intent was that the waste would then be transported to reprocessing or storage sites. However, political opposition to storage site location and safety challenges for reprocessing have led this to be a major social problem. Nuclear waste, first of all, you have to make sure that it is sealed properly. It can't leak. You don't want it to get into groundwater, into the environment. Then that has potential risks for everyone involved. Our ecosystems, animals, people. You also have to make sure, because of the time factor, these things have very, very long half-lives. And then there's the risk factor. You don't want anyone to know where your nuclear waste is because then that also makes it a target for acts of terrorism. Nuclear fusion, much different from fission, is when you're combining smaller atoms and a lot of energy is released. There's more energy released in fusion than in fission. This occurs naturally on the sun, and the reactions are often called thermonuclear reactions. If it were possible to easily produce this type of energy, it would be a preferred source of energy. However, there are problems, and that is because it takes extremely high temperatures and pressures in order to cause the nuclei to fuse. This was achieved using an atomic bomb to initiate fusion in a hydrogen bomb. But obviously we know that this isn't an acceptable method of producing energy. Here they took deuterium 21H and tritium 31H to produce helium and a neutron. We are constantly exposed, whether we know it or not, to radiation in the environment. Ionizing radiation is more harmful to living systems than non-ionizing radiation, such as radio frequency and electromagnetic radiation. Most living organisms are greater than 70% water. Ionizing radiation is what causes water to ionize. When that happens, it creates unstable OH radicals, which result in cell damage. So here you can see, you all know, we've already been through this. You know this reaction. Water is amphoteric. It can be a proton donor, a proton acceptor. So here you're creating hydronium ions and OH radicals. The damage at the cellular level depends on the type of radioactivity, the length of exposure, and whether the source is inside or outside the body. Three big things. Outside the body, gamma rays are the most dangerous. Inside the body, alpha radiation can cause the most harm. Remember, gamma rays have a 10,000 time penetration power. They can go through skin, tissue, and bone. It's similar to what's used in X-rays, which is why we use a lead shield when they take X-rays. Beta can get through skin. Alpha has a hard time getting through skin, but if it's inside the body, it's going to cause the most damage because it affects mass and charge. So what amount is safe? Well, you have to look at standards. What are the standards for safety? Getting people to agree on what that should be is very difficult. Another thing to consider, low level but long-term exposure can still cause health issues. Damage to growth and regulation mechanisms of cells results in cancer. So let's look at some average abundances and activities of natural radionuclides that we are surrounded by. So the four top are potassium 40, rubidium 87, thorium 234, and uranium 238. Where are they found? All over. Land, ocean, and human body. Now, the last one you see here in the bottom right-hand corner, 0.4 plus on the uranium-238 in human body activity. That value also includes lead-210 and polonium-210, which are daughter cells of the uranium-238. And that shouldn't say uranium. I knew it didn't make sense. It's uranium-238. That's a typo in the slide from the company. Also, what you should look at is the units. Some of these are parts per million. Some are in Becquerel per kilogram, milligram per liter, Becquerel per liter, or just Becquerel. And so you have to take them out of context. But eventually, prolonged exposure, even to small amounts, can have an effect on the body. So two units commonly used to measure exposure to radiation are called the Gray, abbreviated GY, and that shows absorption of 1 joule of energy per kilogram of body tissue, and the RAD, which stands for radiation absorbed dose, and that's the absorption of 0.01 or 1/100th of a joule of energy per kilogram of tissue. So that you can understand how those two are related, 1 Gray is equal to 100 rads. Now, I'm sure it should make sense to you that not all forms of radiation harm tissue equally. So then we have to look at something called relative biological effectiveness to determine how much biological effect there is, A, depending on the tissue, and B, depending on the source of radiation. The effective dose is called the REM, and the SI unit is sievert. So 1 sievert equals 100 rem. The number of rems is equal to the number of rads times RBE. So the relative absorbed dose times the relative biological effectiveness. So 600 REMs is fatal to most humans, and average exposure per year is 360 millirems. So let's look at the effects of short-term exposure. So if your REM is between 0 and 25, then there's no detectable clinical effects. 25 to 50 could be slight or temporary decrease in the white blood cell count. 100 to 200 is marked by nausea and a more drastic decrease in white blood cell counts. And 500, an REM of 500, is death of the half of the exposed population within 30 days. So when we talk about short-term exposure, most of that comes from natural sources, rocks and soils, cosmic rays, radioisotopes in the body, maybe from, medical diagnosis, and that is measured in millirems. the highest of that being radon, which I didn't even talk about. The rest comes from human-made sources, medical x-rays, so that's 39 millirems, nuclear medicine 14, and 11 in consumer products. Now, notice medical x-rays 39 rem. If you go back to the previous chart that we just looked at, up to 50 millirems causes a slight effect in the body and a decrease in the white blood cells. So we've all gotten x-rays. So we've all been victims of this. What's the important message here? Like, you shouldn't be x-raying your body every week, okay? You know, if you're getting an x-ray a year, it's not going to have a long-term effect on you. If you're x-raying your body once a month, that's a different story. That might be something that you want to look into. So this second PowerPoint, we went into more detail. We never really talked about, you know, radiation, exposure, how fission and fusion really work in regions chemistry. But again, this is some more, I would say that it's more conversational information and to make you aware of what's happening out there. So at this time, if time permits, you can work on the questions, the practice questions that I gave you, and then you can also work on the chapter problems after the practice problems. If not, you can begin them next class, and I'll also have another lesson for next class, and then next week we'll go back to doing some labs. Thanks, guys, and if you have any problems, you know how to get a hold of me.